Hi, everyone. My name is Mandela Patrick. I'm from South Trinidad, Palmas in particular. And yeah, I'm excited to have all of you all on this webinar today. It's a super exciting topic for me. It's what I'm currently doing my PhD in. And I think it's the present and the future, and sort of felt it was a good opportunity to sort of expose this technology more broadly to people from the Caribbean, particularly from Trinidad. And yeah, I'm excited to have you all on board. So buckle tight and yeah, get ready. So I'm gonna share my screen. Um, can you all see my screen? All right, sweet. So yes, so can you all see my screen? Can you all give me a thumbs up if you all see my screen? Perfect. All right, sweet. So yes, so this is going to be the first lecture is going to be an introduction. Introduction to deep learning. And so let's start. What is deep learning? So broadly, we have this sort of this broad term artificial intelligence. And fundamentally, artificial intelligence is any technique that enables computers to mimic behavior. So when you think of a human, you think of someone who can talk, who can see, who can converse, who can think analytically. And any sort of technique that allows computers to achieve this objective is sort of what we describe as artificial intelligence. And then if we go a little deeper, we have machine learning, which is specifically how do you achieve this explicitly with only using data. So instead of symbolic AI, which was sort of the paradigm before, where you would have to sort of hand define specific rules on how you want a computer to learn. Now you just give the computer a bunch of data and it figures out on itself how to sort of mimic human behavior. And then you go a little deeper and then you have what we call deep learning, where specifically we use these models we call neural networks to achieve this objective. So the lecture schedule is as follows. Today we're going to cover introduction to deep learning, and we're going to have a Q&A by Nyla Murray, and then some coding exercises to sort of get you familiar with this language, this framework we call PyTorch, which is a popular deep learning framework that is used by both academics and industry professionals. And then Tuesday we have deep sequence modeling, the Q&A by Nicholas Murray, who is head of cloud infrastructure at IBM Research. And then we'll be doing some coding exercises where we train models to understand the sentiment or emotion of language using recurrent neural networks and BERT type models. On Wednesday, we focus more on computer vision, where we train computers to understand the visual world. And then we'll have a Q&A by Daniel Belgrave. And from a coding exercise, we will learn how to do image classification and detection using convolutional neural networks. Thursday, we have deep generative modeling, where we train convolutional neural networks to generate images such as photorealistic art and faces. And then finally, on Friday, we end off with a bunch of deep learning applications where we see how Trinidadians, both locally and abroad, are applying this technology to advance quite a few areas. So the core staff, I'll be the head lecturer, and these are the amazing, amazing panelists who will come and give Q&As. This is an incredible opportunity, so please use the time. There's going to be opportunities for you all to ask questions, so please take advantage of that. These people have a wealth of knowledge, and it's an incredible opportunity to sort of glean into their thoughts and any advice that they may have. And I want to say thank you to our sponsors, BP Trinidad and Tobago. And Rachel will say a few words on behalf of BPTT. Rachel, are you on the call? Rachel? Okay, let's move on. So why deep learning and why now? So traditionally, before what we had was hand-engineered features. And what we mean by hand-engineered features is that we sort of think of important concepts that we think are important to understand some, say, image, and we sort of hand define how to describe these features or concepts. So if you, for example, you think of understanding human faces, all human faces have, for example, say eyes, they have a mouth, they have a nose, and what you would have to do before was try to describe what is an eye. And I don't know how easy it is for you, but describing an eye in computer language is non-trivial. And you have to basically define and specify these different sort of what we call features to understand different concepts. And that is only, say, for example, faces. When you want to, say, classify the millions of objects we have in the world, hand defining features just doesn't become scalable. It's very time consuming and it just doesn't work in practice. So what deep learning has been able to achieve is that we can essentially learn the underlying features directly from the data itself. And as I said, features are just what we call like concepts that are important to classify or understand the content of an image. So for example, eyes, nose, ears, and then just general facial structure. And as you can see, you could build up what we call a hierarchy of features. So you have low-level features, such as edges, such as circles, more mid-level features, such as eyes and nose. And then when you go on a higher level, you have stuff like just general facial structure, etc. And why now? So a lot of these technologies and concepts have been around since the 1950s. Stochastic gradient descent, which you need to sort of train these neural networks, and sort of the underlying convolutional neural networks, multi-layer perceptron, they've been around since the 80s, the 90s. So why now? Essentially, a collision of three main factors. So we have big data, where we have these massive data sets, which has been facilitated mostly due to the internet. So you have sources such as Wikipedia, which has this large library of just human knowledge and human text. ImageNet, which is a popular image data set, which has facilitated the growth of this field, because these models are extremely data hungry. So the growth of data has really facilitated the advancement of the field. Then hardware. So a lot of neural networks relies a lot on what we call matrix multiplication, and graphic processing units has allowed us to do this much more quicker. And the speed and memory of these graphical processing units has increased sort of exponentially since the 1950s, 80s, 90s. And then software. So for example, in this course, we're going to be using PyTorch, and libraries such as PyTorch and TensorFlow have made it pretty easy for you to run these models and train these models on the standard graphical processing unit and machines. So the perceptron. So this is the smallest building block of a neural network. And at its core, it's like pretty simple actually. So what you have is what we call the inputs, and you have X1, X2, X3. And you essentially want to weight each aspect of the input. So you have W1, which assigns a weight to feature 1, W2, which assigns a weight to feature 2, and weight 3, which assigns a weight to feature 3. And what that essentially you could think of is assigning a sort of like importance score to this particular concept or feature to understand what is happening in this image or in this piece of text. So for example, if you were trying to classify faces, and X1 was a feature of i's, we would weight that pretty highly. While, for example, if x2 was a less important feature, for example, let's say just say like color or texture, we weight it lowly. We give it a lower score. And after we weight all of these input features, we just sum them. And then we apply this thing which we call like non-linearity, which allows us to find nonlinear structure in the data. And then that we output some value y prime. So if you look at the equation, it's pretty straightforward. So you have xi, which is each of your input features. You weight it accordingly. You add it up, which is a summation sign. And then you apply this nonlinear activation function, which transforms the data into a nonlinear space. To be more precise, we also add a weight. We also add a bias term, which we give 1, and we have assigned weight W0. So now the equation becomes W0 plus the summation, the weighted combination of the features and the weights. We apply a nonlinear function g, and then that gives us our output y prime. So usually we represent our input as we call vectors, and all vectors is a collection of numbers arranged in a particular order, and it's represented usually in sort of squared brackets, and each of the individual values separated by a comma. And our weight matrix is multiplied by x, and you do this, it's a dot product, you do the same sort of addition. So it's w1 by x1 plus w2 by x2 to wxm by xm. We apply a nonlinearity, and then we give that as our output. So one common activation is what we call the sigmoid function. And what that essentially does is that if you get any output, it squashes in the range between 0 and 1. So for example, if you look at the curve, it's an S-shaped curve. So as you go to negative infinity, the value is 0. And as you go to positive infinity, the value is 1. So as you go along the x-axis, the values, the y-axis values always stays between 0 and 1. And there are common other activation functions. So we just talked about the sigmoid. Another popular one is what we call the ReLU activation function, where every x value less than 0 is assigned 0. And then I look at the blue line, any value that is greater than 0 is assigned to itself. So if the x value is 1, the y value is 1, x value is 2, y value is 2. So you have this what we call like hinge shape of the graph. So the importance of activation functions is what we call to introduce nonlinearities into the network. So a linear function is any function that is basically what we call a straight line. And if the data is what we call linearly separable, we can just draw a straight line and be able to separate the points. But if you look at the red and the green lines, if you try to separate it by any straight line, it would not do a good job of being able to separate the red and the green points. So that's the importance. So what we say is that this data is fundamentally nonlinear, and we need to then introduce nonlinearities into our network to capture this nonlinear structure of the data. So as you can see to your left, the blue line is what we call a linear line, and it's a linear function, and it can only separate stuff along a straight line. And as you can see, it doesn't do a good job separating the green and the orange, and the red, because the data is not linearly separable. So we have to introduce nonlinearities to capture the sort of nonlinear structure of the data, where we can then now be able to separate the red and the green dots on the graph. So let's go through a simple example. So let's say we have two features, x2 and x3. We weight each one, we assign weight 3 to x2, assign weight w2 to x3. And then we have our bias weight term 1. So we represent our input as x1, x2. Yeah, we represent our input as x1 and x2, and then we multiply it by the weight. So you have 3 by x1, and then minus 2 times x2. Sorry for the typo, it's supposed to be x1 and x2 there. And then we add 1, and then we apply the nonlinear function, activation function g, and that gives us our output. And then you have, so basically that can be essentially be represented by a line on a x1, x2 plane. And given some new point w minus 1, 2, we plug it into our equation. So x1 is minus 1, 3 times minus 1 is minus 3. Then minus 4 plus 1 is minus 6. And then if you apply the sigmoid activation function, we get 0.002. So what essentially that does is that it then allows us to create this sort of linear boundary, even though the data, underlying data is not particularly linear. So as we said, the perceptron is the basic building block of the neural network, and it's fundamentally, for the most part, pretty straightforward. We have some inputs, we weight each input, we sum them, we apply a nonlinear activation function, and that gives us our output. And let's a recap here. So as I said, we have our inputs, x1, x2, x3. We multiply it each by a weight, w1, w2, w3. And then we add our bias function, bias term. We sum them, apply a nonlinearity, and that gives us the output. And that's represented above as in its matrix form. But fundamentally, it's a sum plus a nonlinearity. And we can simplify it in this form where, as you see again, we do a weighted sum plus we add a bias term, and that gives us our output. And all a neural network is just stacking a bunch of these units together. So before, where we just had one unit, now we just add a next one, and it's the same operation. So you have a weight for each input, we sum them, we multiply the weight by the input, we sum them, apply a nonlinearity, and that gives us the output. And we do that for both Z1, and we do that as well for Z2. A single layer neural network is essentially, so as you can see the progression, so before we just had a perceptron, which is just one unit, we add another unit, which is a little more complex. And then now for the most basic neural network, we add basically 6 units. So we call this a single layer neural network because it has one hidden layer, and it's hidden because we don't directly see the outputs of we don't directly see its outputs. We see the input, we see the output, but what happens in between, we don't directly see, so we call it hidden. And we measure the depth of the neural network by the number of hidden layers it has. So in this case, because there is only one hidden layer, we say it's a single layer neural network. And it's the same, like each perceptron just does the same thing. It takes the inputs, it weights the inputs, it sums the inputs, applies a nonlinearity, and then outputs a value. And then that becomes, and then it just keeps on going down the chain, fundamentally. And then for a deeper neural network, we just keep stacking these hidden layers. So we just keep on adding more and more layers, and that's fundamentally at the heart of a neural network. So the major takeaway is that a neural network is combined of these simple perceptrons, and all they do is they take some input, they weight the input, apply a sum the weighted combinations of the inputs, apply a nonlinearity, and you just keep on stacking a bunch of these perceptrons as deep as you possibly can. And that's a deep neural network in summary. So let's try applying these on like a basic toy example. So will I pass this class? So you have some input, and as we said, the input is, let's say, in some feature space, X1 represents the number of lectures you attend, and then X2 represents the hours you spent on the final project. So basically the task is, given this input, what is the probability I pass this class? So we could represent this on a 2D axis where essentially the position on the 2D axis gives you the X, basically X1 is the number of lectures you attend, and X2 is the hours spent on the final project. And the color of the dots tells you whether you pass or fail the class. So as you can see, this is a pretty simple classifier, because it seems that the more lectures you attend and the more hours you spend on final project, the better your probability of passing the class. So given this new point, do you think the person is going to pass or fail the class? And in this case, just looking at the structure of the data, we could probably guess that this person is going to pass the class. So this person, 4-5, means that the person attended 4 lectures and spent 5 hours on the final project, X1, X2. And we could just build a neural network to solve this problem. So our input is 2-dimensional, so we have X1 and X2. So 4 is X1, 5 is X2. It is passed through a hidden layer of size 3. And then we have some final output layer Y1, which predicts the probability that you'll pass the class. So the neural network predicted 0.1 or 10% chance that you pass the class. But the actual probability is more like 1, because as you saw from the graph, it's the more lectures you attend and the more hours you spend on your homework, the more likely you are to pass the class. So in this case, the neural network predicted the output as 0.1, which is fundamentally wrong. But why would it? So to quantify this, we define what we call a loss function. So for example, if you think about you're doing you're doing, say, like a homework or any sort of exam, the maximum score you could get is, say, 100%, and then the score that you get is, say, X%, let's say like 75, 80%. Ideally, you want 100%, and that delta of 20% is the difference between what you got or what you predicted and what is the optimal. And that is fundamentally what all a loss function is. It gives you the delta, or it quantifies how much your prediction is off from what we call the ground truth or actual result. And there are different loss functions which are appropriate for different types of data. And usually we have to do the loss function over the entire data set. So per example, we calculate the loss, and then we sum it over all the examples in the data set, and then we take the mean. And this is what we call the empirical loss, because it's the total loss averaged over the entire data set. And as I was explaining, there are different types of loss functions, depending on what kind of output and what kind of data do you have. So in this case, if we want to compare different probability distributions, we use what we call the cross entropy loss, which compares 2 vectors that are between 0 and 1, and they are probability distributions. While, for example, if we are looking to compare real numbers, or real numbers are basically, let's say, non-decimal numbers, basically, we just take the arithmetic difference. So yi is the actual, the predicted value. So in this case, so say fx is 30, that's what the model predicted. The ground truth is 90. So 90 minus 30 is 60, which is the loss for that example. And then for the second example, the model predicted 80, which is f of x. The ground truth is y, which is 20. The difference there is 60, and you square that output, that gives you 360. And you do that for each example, you add them up and you find the average. So important thing to understand is that the reason why this neural network gave us a very bad output, because it has never been trained. What that means is that, just imagine you just like show up for some big exam and you've never practiced before. You just like show up, never, you don't even know what exam you're taking. You don't even know what's on the, what subject it is on. That's basically an untrained neural network. If you just give data to a neural network, it's just not going to magically understand the data. You have to what we call train it. And in the case of, say, like in a sort of educational example, is like a teacher giving you a bunch of homework or practice problems. So you do your bunch of practice problems, and then afterwards you're like, I get the hang of this. And then eventually when you take your end of term exam, you have a better understanding, and you can now do well on the end of term exam. So that's basically what we call training a neural network, is that is basically giving the neural network a bunch of homework, a bunch of examples, to can understand the data, understand how to do the problem. And then when it's ready to go, you could just use it to actually do useful stuff. So how we train a neural network is that we want to find what we call the network weights that achieve the lowest loss. So as we were showing here, is that each of these connections are what we call weights, and they define how important this feature is for the final output. And then we need to find the optimal sets of weights that are able to give us the right output. So that is essentially what the task we're trying to solve. So we have some loss function which quantifies how well or how bad the neural network is doing at its particular task. And then we want to find the weights that gives the lowest loss. And the lowest loss means that it gives the best performance. So we want to find the weights that give the best performance. And that is what this says. And a loss function is, you could think of it as like this like very complex thing, where essentially you have your weights on the bottom, which and then you have on your z-axis, or on your sort of vertical axis, you have the value of the loss, and you want the lowest loss value. So you want to get here at the bottom, that's the lowest loss, and you want to get there. But currently you are starting here. So how do you get to the bottom? So what we do is you randomly pick an initial starting point. So how I think about this is that, for example, let's say you're trying to, I don't know, do some hike. Let's say we're doing a hike, for example, and you start where you start at the entrance, and you eventually want to get to, say, the beach. Say you want to go to Paria Beach or Paria Waterfall, for example. But you start at the beginning, but you don't have some map. So all you could essentially do is just what we call, in this case here, we compute a gradient. In the case of, say, like hiking, you sort of just like trying to follow the trail. And a gradient just basically gives you an idea of, let's say, the trail of a lost landscape. And then we take the direction opposite to the gradient. So the gradient tells you how to go up. We want to go down. So we go in the opposite direction to where the gradient is telling us. And we keep just following the gradient until we hit the minimum loss. So in hiking terms, we start at the beginning and we keep just like following the trail, trudging along until we reach our destination. And that's fun. And you measure your destination because you reach the point which is either highest or lowest point, and it's a similar sort of thing that these neural networks are trying to do. So to reiterate, we initialize the weights randomly, then we compute the gradient, and as I mentioned, the gradient goes uphill. We want to go downhill, so we do the negative gradient, and then we update the weights, and eventually it would converge, meaning that the weights doesn't improve, the loss doesn't improve anymore, and then we return those weights. And so the question is, how do we calculate the gradient? So we do this thing what we call back propagation, which people more familiar with calculus is just essentially applied application of the chain rule. Essentially you want to find how much this weight affects your final loss, right? So you have, in this case, two weight values, W1 and W2, and you want to see how much this W2 affects the final function JW. So we're going to use the chain rule. So we get the gradient of the final, if this is, for some people who are not familiar with the sort of chain rule, or this is not totally necessary. This is just for those to get familiar with the more deeper math. But essentially you find the gradient of Y with respect to the final loss, and then of W2 with respect to Y prime. And as you can see, it cancels off. The delta Y prime cancels off, giving you back your original. And then similarly, we apply the chain rule again, and that gives us the gradient of W1 with respect to the loss function. And you keep doing this repeatedly for all of the weights in your network. But the important thing to get is that, like, fundamentally, we are just calculating gradients. A lot of these modern frameworks, such as PyTorch, does this for you automatically. So you don't need to go into the nitty-gritty, but it's good to get just a high-level understanding of what's going on in the background. So how do we optimize these neural networks in practice? As we sort of mentioned, it's this very much complex landscape. Think about Mount Everest, not too bad, not that bad, but it's probably a good mental picture. And these can be difficult to optimize. In particularly, the learning rate is one of the most important values we can set. The learning rate defines how big our steps to take. So for example, if you're doing this hiking example again, if you go down the wrong path, you could end up in the middle of nowhere. So you want to have a balance of sort of being confident in the direction that you're going, but also being sort of cautious. And the learning rate is a parameter that sort of sets this for a neural network. So in this case, if we set a small learning rate, we're taking like very cautious steps. So it's imagine you have this very long hike and you're just taking very tiny steps. It's going to take forever to reach the point that you want to reach. However, if you just take massive steps, you just go on a whim, you just end up all over the place, and you mightn't reach the destination that you're looking for. While if you sort of do the right learning rate, you sort of quickly, but also in an efficient manner, end up to the point that you want to end up. So how do we set the learning rate? So one naive idea is just to try a bunch of different learning rates and see what works. But a much better idea is to design an adaptive learning rate that adapts to the sort of data and landscape that you have. And these are what we call adaptive learning rates. And these sort of adapt to how large the gradient is, how fast learning is happening. And there are a few optimization algorithms that sets the learning rate for you adaptively. The most popular one being the Adam optimizer, which is the sort of standard. Another thing that we need to consider in neural networks is mini batches. So before when we were describing gradient descent, we were looking at the entire data set at once, which is computationally expensive, particularly for like massive data sets. So what we can do is do stochastic gradient descent, which is just looking at a single data point and computing your gradient based on that. But that is pretty noisy. It's easy to compute, but it's pretty noisy because you only have one example to make your sort of decision. While with mini-batch gradient descent, we look at a batch of data points. So you have, it's fast to compute, but it also gives you a better estimate of the gradient. So it's like, it's sort of, for example, your sort of batch defines how much examples you look at to calculate your gradient. And it's simply like, if you have more data, it's great, but it could be too overwhelming. Too little data, you're like, I don't have enough information. And then just right is probably in the middle. And that's what mini-batch gradient descent allows you to achieve. Another problem we have is the problem of overfitting. So like to give you an example of overfitting, so some of you will probably have done, say, CSEC CAPE, and an example of overfitting is, for example, you study all of the practice problems from 2020 to 2005, and you assume that the 2021 CAPE exam is going to be exactly like the problems that you practice on. So that's what you overfit to your training data. And at that point, like if the exam is different to what you practice on, you're probably in big problems. So that's what we call overfitting. Underfitting is where you probably practice, you just do one practice exam and you're like, I'm fine. And then basically you didn't practice enough. So that's what we call underfitting. And then appropriate fitting, you probably do like 5-7 practice exams. You do a couple extra exams from like your textbook, you do your teacher problem. So you sort of have a more general understanding of what's going on. And you no longer overfit to the data that you trained on, because during test time, you have seen a wide variety of training data. So what we describe that in more technical terms is what we call regularization. And that allows us to improve the generalization of our model on unseen data. So before, where we just only know the training data really well, we know the practice problems really well, but we could also do really well on an exam we've never seen. And that's what we call applying regularization to give you generalization capability to the model. So one simple way to do that is drop out. So essentially, we just drop parts of the network. We drop parts of the network, and what that does is forces the networks to not rely on particular units as often, and it allows it to generalize really well. So similarly, it's like if you sort of just see a bunch like practice, essentially have a variety, you get you solve the sort of generalization problem. And then the last regularization approach is early stopping. And here we just essentially stop the training before it has a chance to overfit. So essentially you have your training error, which is in orange, which is supposed to go down. You want your loss to decrease. And then you're also measuring what we call your validation error, which is your loss on a validation data set. And then when you want to sort of stop training, when essentially you keep on doing good on your training data, but you start doing badly on your validation data. That means you're sort of overfitting to the training data, but not generalizing well to the validation data. So in summary, the perceptron is the basic building block of a neural network. And then when combined with nonlinear activation functions, we're able to learn the nonlinear structure of the data. A neural network is just a bunch of perceptrons stacked together. And then we have to learn the weights of this neural network through backpropagation and gradient descent. And then these neural networks are not trivial to train. So we have to do a bunch of different techniques, such as adaptive learning, mini-batch gradient descent, and regularization to improve the generalization capability and ease of training of these models. So I think that is it from a lecture point of view. I think now I'm going to introduce Nyla Murray for the Q&A. So so how the Q&A is going to work is that I'm going to essentially ask a few questions at the beginning, but then the audience will have the opportunity to ask any questions that they feel like. I'm supposed to ask a question in the Q&A section of Zoom, and then I will ask the question to Nyla to make it easier. But it's an incredible opportunity. She's, to give you an introduction, Nyla is currently the head of AI research at Naval Labs, which is one of the big AI labs in the world. It's based in France. She did a PhD in France, undergrad at Princeton, and is one of the most successful researchers out there. So I'm excited to have her here today. And yeah, welcome, Nyla.
Hello. Hi, everyone. Oh, let me see if I can stop my video. Oops, I can't. Mandela, if you like, you can try to stop my video. You can let me. Otherwise,
Oh, gotcha. Oh. Let me see.
But in the meantime, we can start. Maybe another panelist can do it if possible.
Got you. Yeah. So yeah. So welcome, Nyla. So I think to start, I think what would be great is if you could sort of give a bit of background, sort of where you grew up in Trinidad, what you sort of did for, say, A-level, CSEC, what got you interested in AI, and sort of how was your path to sort of where you're at right now?
Sure. So first of all, thanks for inviting me, Mandela, and thanks for organizing this. As I think it's a really great opportunity that you've spearheaded here. So just to introduce a bit my path. So I am from Arima, Santa Rosa Heights, Arima. Grew up there, went to St. Joseph Girls RC, and then to St. Joseph Convent St. Joseph for O-levels and A-levels. I don't even remember what I did for O-levels, to be honest. But mostly, the science track, if you want to put it that way. And then for A-levels, I did maths, physics, chemistry, and the writing one, I guess, whichever one that is now. I don't remember, general something, I think. It's so funny how things are so important to you when you're in it, and then 20 years later.
Yeah, for sure.
And then so after that, I decided to I was thinking what to do, and I settled on electrical engineering because I felt it was practical enough to get some kind of job after, but not, not so, and still in the kind of area I liked, which was physics. I really like physics a lot, so I thought this would be kind of like a nice equilibrium, basically. And so I went to Princeton to do this. Why did I decide to go to the US? I don't know. I think it just seemed like interesting to try a different kind of model of teaching, to just explore horizons, to do something that was a bit less familiar. So I thought that was interesting, and it was. I think something I enjoyed very much. Just just a different kind of way of different educational style, I guess. And then so while I was there, I did electrical engineering. I got my degree in electrical engineering. During this time, though. I spent a year abroad in Oxford, and it was there that I started to get a taste for what you might call AI, although it was more robotics. So, whether or not robotics is AI, it's a bit complicated. So, you can have discussions about it, but it starts, you start to get this feeling of, okay, having let's say autonomous agents, right? So robotics, you can consider them to be autonomous. That's the goal of robotics. So in some sense, it's related to artificial intelligence, very much so. And so, I did a few courses on things related to robotics and control, and that got me, sort of interested in this field. And then when I was an undergrad, further on, in my senior year at Princeton, I did a course on signal processing and working with what basically I came to realize was computer vision. So computer vision is like the area of AI that focuses on visual perception. So it's kind of like artificial intelligence as applied to and related to visual data, right? So what we do as human beings when we see, how we understand, visual content, what we, the things that we recognize in the world around us, etc. And so that was kind of what piqued my interest, basically, this project I did on this area, which was introduced to me by one of my professors. And then from there, that kind of awakened my interest, and I started to be interested in doing research in that as well. So then I kind of followed on in that path because I decided I wanted to continue to do research. This is something that's very typical. I'm not actually sure how it works in, for example, UE, but I know in the US it's very typical to have a senior thesis where you have to choose a research topic. And my research topic was something related to computer vision. And from there, I really got kind of hooked on it. And I've been doing computer vision basically ever since.
Oh, thank you for sharing that. And then sort of was in terms of sort of the research versus say doing sort of like industry, what was sort of the like say that sort of dichotomy for you, that sort of decision process for you?
So why did I decide to go into industry? So just let everybody know. So I actually after I finished my undergrad, I spent a year doing in the finance industry. So it's completely different. And, for a variety of different reasons, I decided, okay, I still felt like I needed to scratch a kind of itch in terms of just spending more time learning, basically. So that's why I decided to after a year to go back to do a PhD. And then during my PhD, I had the opportunity to do an internship at Xerox. So for those of you who know, so Xerox is a company that, Xerox is a company that is very well known for photocopiers, but then they have a very rich history of just information management, and especially information management of digitized, let's say, copies, right? So this is very much in the wheelhouse of computer vision. So if you have if you have a photocopy, you can do so many things with that if you digitize it, if you scan it, and then you can do a lot of analysis on top of it. So Xerox is very much involved in computer vision as applied to document analysis. And so I had the opportunity to work with them. And I found industry to be very, very, very interesting for different ways. Like in academia, there's a very traditional dichotomy between academia and industry. One is that on the academic side, you have supposedly more freedom, right? You can choose almost any topic you want, and they can be very esoteric. Whereas in industry, they're more typically a bit more down to earth, a bit more applied, and it gives you maybe more impetus to solve very concrete problems that that if it works well, you can improve the lives and you can improve the services of your customers, right? So that's a different kind of it's a different kind of motivation, and I found that very attractive. The idea of being able to to work on a problem that's a hard problem, a challenging one, and something that will really concretely improve people's lives in the near future if you get it to work.
Got you. And then going on about, I think from sort of like my experience and background, I think mentorship has been sort of a very important part of sort of like my journey and how I've been able to sort of like achieve some of my goals. I'm curious for you, like, what was the role of sort of mentors in your life in terms of navigating sort of these questions? And if you have any advice to share about how people could go about, say, like finding mentors who can be helpful, that would be great.
So yeah, I completely agree with you, Mandela, that mentorship is very critical. It's played a very big role in my life as well, I would say, in my career. I have to say I was never very proactive about it, so I kind of got lucky. I lucked into a lot of mentorship opportunities with people who, took an interest in me, people who kind of, gave me opportunities. But, I guess on my side, what's the part in which I was a bit proactive was just in finding something that really, that I found fascinating and that I enjoy doing, basically. And I think very often, mentors are very willing to help people who they see are very passionate about something. And so that is a way, I think finding something you're passionate in is very valuable. It's something that it seems a bit, sometimes you might see, okay, it's not practical. You can't, you can't be passionate about everything you do in life. But if you get an opportunity to find an area you want to work on that really fascinates you, then that's, people see that in you and then they want to help you automatically. And then, I do think it's even better if you can be proactive about that. And that's easy to do, I think, if you have an area that fascinates you, because then you can reach out to people who are working in the same area, say, I really like your work, have a interesting conversation with them or start up an interesting conversation with them. And they will naturally, especially in research, people do research because they're passionate. So if somebody else comes to you and says, I find the work that you do very interesting, I'd like to talk about it more with you, then more often than not, that person is going to be very willing to help you because, they're passionate about the same topic. So you have something in common. That's very important to both of you. So I would say basically finding an area that is interesting to you and then reaching out to people with similar interests. And from there, mentorship opportunities hopefully will come up.
Gotcha, that's amazing. So I think I'm going to open it up to the audience to see whether they have any questions. If not, I could ask a bunch of questions afterwards. So I think there's a question from Stephen Gould, and it was, what was your main thematic area, I'm guessing, in research?
Sure. So I've covered a couple topics. So during my PhD, I worked on what you might call subjective visual perception, and how can you create computational models of subjective visual perception. And so what is subjective visual perception? That refers to, let's say, like somebody's visual experience that is somewhat unique to that individual. And so to give a contrasting example, normally if somebody sees like if you're looking at a landscape scene and you see, okay, there's a house over there, there's a cow over there, then mostly everybody would agree with that, right? But there's certain visual experiences that are subjective, meaning that it can vary from one individual to the other, and there's no one right way to have a certain experience. So I looked specifically at things related to visual aesthetics. So understanding what's about some kind of visual stimulus, like let's say, for example, an image. What about that would be attractive to somebody? Would somebody consider this to be an aesthetically pleasing image or not, and why? So I looked into those kinds of things from a computational way as opposed to psychologically. And then I also looked into what we call saliency or bottom-up visual attention, meaning if you look at the scene, what drives people's attentions? What would somebody look at if they were looking at a scene? What would attract their attention and why? So one typical example is very often humans like to pay attention to other humans. So if you have a scene and there's a human being in it, most likely you look at the human, and there may be many things in the scene that you could potentially pay attention to but that you wouldn't. So that was my main area. And then after that, I started to look at things that are a bit more objective, specifically an area called fine-grained visual recognition. So that is understanding it's creating computational models to recognize objects in visual scenes, with a particular focus on distinguishing between fairly similar objects. So a typical recognition problem is to be able to categorize a scene as containing a cat versus a dog. And if you want to do fine-grained recognition, you want to focus on whether the dog is a poodle or a chihuahua, for example. Hey, Manuel, I don't hear you. Maybe you're muted? Yeah.
Yeah, there's a bunch of questions, so let me start going through them. So from Tariq Mohammed, any advice for future PhD candidates?
Okay, any advice for future PhD candidates? Good question. I would say what's very important is, I think, a mentor, and I think an environment, a research environment that is that you're comfortable with. So I think it's important to, especially nowadays where, especially in computer, AI, let's say in general, is very collaborative, and I think you go farther if you're collaborative. So I think finding a lab where you can work with other people as opposed to where you're struggling by yourself, I think it will be a more productive, more fruitful, and more, I think, enjoyable experience. So I think trying to find a lab where you have the impression that people collaborate a lot. If you look at papers that come out of this lab, are they typically papers with just 2 people or papers with 5? I would suggest to go to a lab where you have 5 people on a paper. I think you learn more because you work with more people and you just learn more rapidly. And then also having a supervisor that you're very comfortable with. It's very important to have the right supervisor, I think. Somebody who truly appreciates who takes the role of mentorship seriously. I think that's also something that's very important. I would say even more so than the topic. I think the topic is probably not even the most important thing. I think the first 2 things I mentioned, I would say are more important.
Next one from Diochan Bridge Mohan. How can you sort of get involved in AI without, say, leaving Trinidad, given I have a background in sort of control systems and automation, etc.?
So, I mean, there's AI in UE. So, I mean, I can put you on, if you're interested, I can put you on to people I know who are doing computer vision, for example. I know a professor at UE who's doing computer vision. And then, but that's on the research side if you want to do it, academically. But of course, you can do a lot of AI in terms of just doing hobbies, thinking about startup ideas. And there's just so much content online related to this. So if you're interested just in doing AI to learn about it, first of all, and then maybe eventually to, I don't know, come up with a cool product or something, then there's a lot of material online. There are websites like towards data science or deep learning I think AI. There are just many online communities where you can learn a lot. You have tutorials where you can get started. And I'm sure if you ask Mandela afterwards, he can point you to some resources. So yeah, I would either you can do like the informal path as I just mentioned, or there are opportunities to work with people. And then there may also be opportunities to work remotely with people as well. I think it's a kind of field where you can reach out to people whose work and work that interests you, and you'd be surprised the kind of collaborations you can have, even if you're not in the same physical place.
So there seems to be a couple of questions on robotics. So I think one was about directly applying deep learning to robotics, and can you go a little more into the sort of differences between robotics and AI?
Sure. So artificial intelligence is very tricky, and I'm not even going to try to define it here, right? It's something that people have a lot of fights over what does it really mean to be, to have artificial intelligence? What even is intelligence, right? I think the relationship between robotics and artificial intelligence is that the dream of robotics are to have like autonomous agents that interact with their environment, right? So basically you want to have a robot that is given some goal. It doesn't have to be self-directed goal. It could be a goal given by a human, for example. But then once this goal is given, some sort of high-level goal, is able to accomplish it while interacting with the environment in some way, right? So that could be things like that are obvious, like navigation. It could be even something like controlling the temperature. It can be like a Roomba that's moving around vacuuming. So all these things have a notion of autonomy, which is, I think, what people consider somewhat fundamental to an artificial intelligence. However, I think when people think about artificial intelligence, number one, there's not necessarily a notion of interacting with your environment, modifying, for example, your environment or taking input from your environment. Not necessarily. You can be artificially intelligent without having that part of it. Because an artificial intelligent agent could be completely virtual, right, and live in a completely virtual world. So I would say like that's a major difference. I think also when people think of artificial intelligence, they think of some notion of, especially nowadays, it's kind of linked with learning, like machine learning, right? Which is it's also not equivalent, right? So there's a lot of machine learning that's AI, you would say, but it's not the same. A lot of what we call machine learning is basically statistics. Is statistics artificial intelligence? I wouldn't necessarily say so. And I think robots don't necessarily have to learn from data. So that's another kind of distinction that I would put there. But the margins are quite blurry, right? So I think there are ways in which they're quite similar and ways in which they're somewhat distinct.
Sweet. I think a couple more questions. So I think from Glenn Goddard, what are some of the moral dilemmas that you come across in AI, and how can sort of minorities be impacted by weighting factors and other aspects?
So I think the major issue, once again, this can become very philosophical. I'm not an expert in ethics of AI. Like when I think about, okay, how has it impacted me, or how have I thought about it? It's in terms of when we think of who will be impacted by this technology, we have to be the challenge is to really include all the relevant stakeholders. So I think very often AI systems, and this is not unique to AI, this is unique to pretty much all technology, right? But AI is I think it's a technology that is emerging. And so I think people see this as an opportunity to try to get it right this time, but I don't think, it's unique in that way, right? And the challenge I'm mentioning is to make sure that people who will be impacted are taken into account and are involved in the design of some artificial intelligence system from the beginning, right? So very often historically we develop some system, and then 10 years later we realize, okay, there's this horrible effect that we didn't foresee, and let's try to patch, put a solution to it that doesn't work after the fact. And so the challenge now is to try to get everybody who's at stake, who has a stake in it, in the discussion at the beginning to understand like potential blind spots that we don't see. And that's a challenge because there's a tendency now to just move very quickly to try to take advantage of this technology. Everybody is trying to win this arms race basically. And that means that people feel like we don't have time for this time of reflection. And that's the challenge, to take the time to do it, to take the time to involve everybody who will be impacted. But I see this as a challenge, not with the technology yet. It's a challenge with basically, with setting the right kind of ethical boundaries and structures.
Sweet. I think the final question, which I think is probably, it seems like a lot of the questions seem to be focusing on, is just generally, do you have just general advice about sort of like getting into AI? It seems like a lot of the questions focus on like, I am doing electrical engineering or I'm doing petroleum engineering. Which subjects is it necessary? Do you need a PhD? So I think a lot of these sort of like more practical questions people would love some insights on.
Sure. So I would say, I think what's most important in terms of just core knowledge for AI is good knowledge. And once again, these are things that you can look into. But I would say a good knowledge of statistics, calculus. For the theory, I think statistics and calculus is probably the two most important things. I'm trying to think of linear algebra, of course. Yeah, these three, I would say this is the trifecta that will give you a very solid base into the theory of this. And then more on the practical side, most of practically, if you're doing it, well, I shouldn't say practically, but if you want to implement stuff, of course, being a fairly good programmer is useful. It's not, it's not, I wouldn't say it's like critical, but it will help you move things faster if you have a good base in software engineering, basically. But I would say more fundamentally, the three things I mentioned earlier are most critical. And so you can get different things, right? You can get that across different types of degrees. So, I think honestly you can do anything for sure. I mean, it would be hard to do like a sociology degree and be able to fit in those types of courses. But I think if you do almost any kind of STEM-like course, you can fit in the relevant courses to get you up to speed there.
Got you. Sweet. I think that's perfect. Thank you so much, Nyla, for taking the time. Really appreciate it. And yeah, I think everyone sort of appreciated the sort of advice you've given. So thanks so much.
Yeah, you're very welcome. And just to let everyone know, if anybody has any other questions they'd like to reach out, I mean, you can feel free to reach out to me. I think you can find my email online, so feel free to reach out if you have any more questions.
Sweet, thanks, Nyla. So now we'll have Rachel from BP to sort of talk about their involvement in the course. Let me see. Rachel, are you there? All right. So we probably wait till later to get Rachel involved. I know there were like other questions. A few of them I could probably address. And I know, Nyla, if you have some time, there are a few other questions.
Sure.
You could probably respond over chat directly to respond these. But I will sort of transition to the coding exercise part of it. So how I wanted to sort of structure this was sort of, you have a 45-minute lecture where you sort of get a general, what, Rachel, are you here?
Yes, I am. Can you hear me?
Yeah, we can hear you. You can go ahead.
Good afternoon, everyone. My name is Rachel Keynes. I work at BPTT and the corporate responsibility team. I just wanted to thank all of y'all for joining this course. Sorry I wasn't able to join earlier. I had some problems with my mic. But we want to thank you. We do think that AI is the technology that the future is being built on, and we really want as many Trinidadians as possible to be exposed to this, because we don't want to be left behind as we move into this digital age. And by the overwhelming response that we got for signups, we know that we're moving in the right direction with our tech education programs. And I'd like to thank all of you all who joined the call. I also want to say thanks to Mandela because, you know, and all the guest lecturers that will be joining us over the course of this week. Because really without them, we wouldn't have a course. And, you know, Mandela is actually volunteering his time to do this. He has compiled everything with his colleagues, or I would say friends in the industry, to bring this course to you. So thank you to Mandela, and I hope that, you know, you all enjoy this course and at least, you know, this sparks your interest in pursuing a career in artificial intelligence. Thank you.
Sweet. Thanks, Risha. Sweet. So let's see how I wanted to sort of structure it was that you have a sort of 45 minutes introduction to sort of like a lecture format of the sort of major concepts. And then we sort of go through and I'll sort of walk you through sort of these coding exercises. And all of these material will be available on the website afterwards, by the way, because there was a couple of questions on that. But I'll sort of walk you through it live about sort of like how this is coded to give you a general sense of how we get these neural networks to work. So let me share my screen again. Yep. So so this thing, so what we are on is this thing called a Google Colab, and what it is, it allows you to sort of very quickly run programs and set up and sort of load in packages very easily. Quickly experiment. It also has access to GPU, to a single GPU that you could quickly train some models on, because GPUs are pretty much necessary to train any sort of neural network, and they are not cheap. So you could sort of get something on Amazon Cloud Services or Microsoft or Azure's Cloud Services, but they cost a certain amount per hour to use, while this is totally free. And to just use a GPU, all you simply have to do is notebook settings, and then you click GPU, and you're good to go. And then to run a cell, you just click the play button, and it outputs the result in the cell below. And then these are sort of like comments or text to get an understanding of the code below. And you will embed images, etc. So as mentioned, the sort of framework that we're using is called PyTorch, which is built on top of Python. And it is sort of a replacement for NumPy. It's basically a GPU-powered NumPy, and NumPy is a mathematical mathematics and statistics library in Python. And PyTorch basically augments it with GPUs, as well as easy and convenient use of functions to train neural networks. So I'm going to walk you through the code now. So NumPy is, as I said, a library that does a lot of mathematical sort of functions. And then Torch is PyTorch. And essentially, both these libraries are built on the fundamental concept of matrices. And matrices are simply just rows and columns of numbers. For those familiar with matrix from sort of basic linear algebra. So if I run this cell, it's just starting up. Right, so this is what we call a 2x3 NumPy tensor. And what that means is that you have 2 rows, this is a row, and 3 columns, and they all fill with zeros. And similarly, you could do the same thing in PyTorch, and you have 2 rows and 3 columns. You can sort of access specific values within that tensor by essentially indexing, which specifies which row and then which column you want to get the value from. So 0, 1 means a 0 and everything starts with 0. Everything is 0 index. So while in normal sort of math, we start with 1, in computer programming, we start with 0. So the 0th index plus the first column would be 0. And we essentially print all these values. And then we could easily go between PyTorch and NumPy. So to convert a NumPy array to a PyTorch tensor, we just do torch.tensor and back. And then we could also use torch from NumPy. And then to go from PyTorch to NumPy, we just do .NumPy. And here we torch.random is the utility function that creates a random value, random values of shape 2. And essentially, as you can see here, we're printing the device that the value is stored on. And it's stored on what we call a CPU, which is the central processing unit. But what we want to do is do our computations on GPU, which is called CUDA. So we could move this to a GPU, and we move it to GPU 0. And then once we print the device of T, it moves, and you print the device now of T. Since we've moved it to GPU, it has device CUDA. And then if we move it back to CPU, we can by using the same convenient to function, and now it's back on CPU. So in this notebook, we're traditionally gonna train what we call a neural network classifier. And this neural network classifier essentially takes a handwritten digit, either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and outputs a label. So basically, the model is trying to classify some handwritten digit into a discrete label, either 0 through 9. And so you have a bunch of data, and you essentially train the model. As we were explaining before, we give the model a bunch of data. We use a loss function and backpropagation to train the weights, and then eventually, given some new digit, it's able to output hopefully the correct value. So we have a bunch of imports. So Torch has a bunch of convenience functions. And then Torch Vision is another PyTorch library that is particularly geared for computer vision. And then we have NumPy and then Pill, which allows you to open images, etc. And then here we sort of create a device on CUDA if CUDA is available, if you have a GPU available. So basically, I try to break up all of these notebooks into sort of 4 or 5 discrete steps. And this is sort of how most machine learning applications on a high level is sort of, you can sort of mentally structure it, is that you want to create a data set, you want to define a data set, you want to define a model or neural network, you want to define the loss function, which we looked at, then the type of optimizer to learn the weights of a neural network, and then we sort of iterate through the data, compute the loss, and update the weights, essentially. So I'm going to take you through sort of each of these steps in PyTorch. So here I am downloading the data set and the MS data set, which, as I said, is basically about 60,000 images, where each image is a handwritten digit, either 0 through 9. And then we have to define what we call a PyTorch data set. And what a PyTorch data set does is that it structures, it essentially has 2 main functions, essentially, or 2 important functions you have to define. It's an init function, which basically does any sort of pre-processing. And then the most important is what we call the get item function, which essentially returns the data in the format that you want. So in this case here, we just read in a bunch of images from, disk, and we structure it into a list. And then the main function that has the get, and then is the get item, which essentially here we like get the image, we get the ground truth label, we apply any sort of image transforms, and we retain the image and the label, right? And then we define what we call a data loader, which essentially batches or creates a batch of images. So it takes, so a data loader takes in a data set, which we've defined here, and it specifies how much examples in a batch, and then whether to shuffle the data, etc. So the training set has 60,000 images and a test set has 10,000 images. So let's visualize what's in the data set. So we randomly take 16 images from the data set and let's output it. So as you can see, these are 16 random examples from the data set and they're all handwritten digits. And essentially what a neural network needs to learn to do is, given some picture of this handwritten digit, can it predict that this is a 6? Can it predict that this is a 9? And like to humans, this is like extremely trivial. By the way, like it's like why do we need to why doesn't the computer understand this out of the box? But fundamentally, a computer only understands zeros and ones. And like this, even though this is like a toy example, a lot of the concepts of that we're learning here is going to allow computers to understand any sort of images, any sort of video content. But we're starting with this sort of handwritten digits because this was sort of the foundational problem that these tech ideas are built on. So after we've defined our data set, we need to define our model. And this is similar to what we were looking at earlier. So we have our input layer, which is, in this case, we have a neuron per pixel. So the image is 28 pixels by 28 pixels. So we have 784 total pixels. And then we have one hidden layer, which we could define. And then we have our output layer and we have our output per example. And so here, as I've showed, input size equals 784, which is 28 by 28. We define a hidden layer size of 1,000. And then you define an output layer, which is basically the number, which is equal to the number of outputs that we want. In this case, we want a probability per output. So whether this is a 1 or 2, 3, 4, 5, 6, 7, 8, or 9. So here we define what we call our neural network. And there are two main functions we need to define: the init function, which defines the layers of our neural network. And in this case, we have, this is our input to hidden layer. So we have 784 units in the input, 1,000 units in the hidden layer. And then from the 1,000 hidden units in the hidden layer, we have 10 output units. And here we define it as a linear function. And then here is our ReLU activation function that we were looking at. And as you can recall from the slides, what we simply do is that we apply a layer and then we apply a nonlinear activation function. Similarly, again, we take the output here, apply the linear layer, and then apply activation function. And then here we move it to GPU because we want everything on the GPU. So we move the neural network onto the device GPU. And then we ever define our loss function. So you remember we looked at the cross entropy loss function, which allows us to compare two probability distributions. So here we define our loss function, cross entropy loss. And then we define our optimizer. Remember when we were looking at the optimizer, we have the optimizer basically describes how to sort of update the weights of a neural network. So it takes in the model parameters, our learning rate, which is basically, remember, it tells us how much of a step we want to take each iteration. And then we have a momentum term, which also sort of calibrates how we step. So we define our optimizer here. And then all we need to do is then what we call train the neural network. So to train a neural network, what we do is we put the model in train mode, and then we define how many epochs we want to go over the data. And an epoch basically defines one loop through the entire data. So for example, if you're doing a homework problem, you probably want to see it a couple of times to fully understand it. Similarly, the neural network wants to go through the data multiple times to fully understand it. So here we define the number of epochs that we want to train the model on. And then we iterate through the data set, and it returns the data as well as the label. We put it on GPU, and we pass that data through the model, and then the model gives us an output score. But we need to train the model, so we need to define the loss, which gives us the discrepancy between the output that the model predicted and the actual ground truth, which is what the model is trying to predict. This loss basically tells the neural network how off it was on its predictions. Then we sort of do loss at backward, which is we call the back propagation step. So given the loss, we update the weights of the neural network. And so here we calculate the gradients, and then here we update the weights using the learning rate, etc. And then we do some prints. And then, yeah, so that's the train loop. And then in the testing loop, you're trying to measure out. So basically when it's training, we need to have like a validation set to see how well it's performing. So we know if to stop it early. So here we're iterating over the testing set. And we print the accuracy of the prediction on the testing set. So here we are about to train the neural network for 5 epochs. And what that means is that we train it, basically the neural network goes through the data 5 times. And you see here, so it's training. It seemed like a bunch of just numbers, but I'll explain the numbers soon. All right. So yeah, so here we are on first epoch 0, epoch 1, 2, 3, 4. As I said, everything starts at 0, and this is 5 epochs, so it's 5 loops to the data. Here indicates, so we have 60,000 examples, and this is here is at 6,400 examples out of 60,000, so 11% of the data. And then eventually it goes through 100% of the data, and it starts over again, and blah, blah, blah. Here's the loss. So the loss, as you said, is basically the discrepancy between what the model predicts and what the ground truth is. And we want to decrease the loss. We want to reach to the bottom of that landscape. Right? So you want to check to see if the loss is decreasing. So it starts at 2.3. It generally is decreasing to about 0.6 on average, 0.5, 0.6, 0.5, 0.6. Yeah. And then, so you can see on the test set, the accuracy increases from 77% to 81%. So as the loss is decreasing, the accuracy on the test set is increasing, which is what we want. And then to verify that the model is actually doing something, we can perform some inference on the model. So let's see. So this is the data, and GT is the ground truth, and PD is the prediction of the model. So for 1, the ground truth is 1. The model predicted 7, which is wrong, but you could see how the model could get confused. Here it correctly predicts 2. Here it mispredicts again. So it seems to be struggling to differentiate 1 from 7. Similarly, it makes an error here, makes another error here. It predicts 6 when it's the 4. It gets 2 correct. It seems to understand 2 pretty well. it gets the 8 correct, it gets the 3 correct, it gets the 0 correct, it doesn't get this 3 correct, it doesn't get the 8 correct, and it makes a bunch of other mistakes with 1 and 7, as we were seeing. So the final accuracy of this model is about 81%. In the lecture on Wednesday, we're going to use what we call a convolutional neural network, which is more designed for images, and it's going to increase the accuracy to basically 99%. But just with the sort of basic building blocks we learned today of perceptrons, and stacking a bunch of perceptron units together, we're able to do a non-trivial task for computers, which is classifying images into digits. So this is sort of, on a high level, the basic introduction. I'm happy to take a bunch of questions. So if you could post in the Q&A or in the regular chat, I will answer any questions that is posted. Let me see if I see any questions in the Q&A. Let me share the link in the chat. So I have a question from, let me see, anyone in the link can view. All right, so I'm posting the link in the chat. So what you'd have to do is, when you get the link, what you do is you click Save a Copy in Drive, and then you could sort of play with it. At the moment, I'm only using it. So people didn't want, so people want me to go through the exercise again. I can do that. All right, so let me go through the questions first, and then I'll go through the notebook one more time. So from David Bailey, how would you get a data to be so regular? As in all the numbers are the same size and orientation more or less. That's a very good point. So a big part of getting deep learning to work really well is pre-processing. So essentially, most times you would have to sort of, what we do is what we call like color regularization, where we sort of subtract the mean and standard deviation from all the images so that the color, there isn't much differences in sort of contrast for the photo. Then we also try to center crop the images to make sure that it's sort of centrally oriented. So a big part of, like, in a practical setting, is the pre-processing pipeline. We wouldn't necessarily go into that in this course, because it's more in like the very nitty-gritty of getting this stuff to work really well. And I was sort of trying to make sure people get a high level understanding of what's going on. So from Aidan, if it's the device not declared, can you just add it? So you need to, so essentially by default, every tensor that you create is on CPU, but you have to move it. You have to move it to GPU so that it's on GPU. Because if it's not on GPU, for example, this, which took like 4 seconds on average per epoch, would probably take like minutes. So that's sort of like one of the convenient part of getting a Google Colab, is that if you go to edit and you go to notebook settings, and you change it to GPU, you could have free access to GPU to play with GPU for your experiments, which is honestly a game changer, and you should take advantage of it. And from Lemuel Pixels, so the pictures are 28 by 28, which is which is why, for example, when we flattened it into a tensor, it's 784 pixels. From ESA, why did you use PyTorch? So over OpenCV. So OpenCV is a library that is specifically used for image processing, but it's not you cannot train it, and it has a bunch of convenient applications for processing images, but it's not for building and training neural networks. So OpenCV is part of a pipeline for training neural networks. So as I was explaining before, I might use OpenCV to pre-process the data before passing it into the neural network, but it's not. It's a part of the pipeline. So from Joel, is the optimizer controlling back propagation or the loss function? So the optimizer controls the back propagation, which is a function of the loss function. So essentially, the optimizer, as you can see here, the optimizer takes the model's parameters and it defines the learning rate. And then if you look in the training loop, what happens? So this part here is pretty standard. So here the optimizer zeros the gradients. So what that means is that it just, for all of the gradients for each model weight, it just zeros it out because it's going to perform this step now. And then loss.backward basically calculates the gradient, which is the gradient of the loss with respect to every weight. And then we optimize that step. Then does what we call optimization, where we update the weights based on the gradient times the learning rate. So let me see if I could show that a little more clearly. So if you're so here, so basically this part here, where is the gradient of the weight with respect to the loss, that is what loss.backward calculates. And optimize that step is when we update the weights we update the weights given the gradient, and then we scale it by the learning rate, which tells us how big of a step we want to take with respect to our gradient. So W is the current version of the weights, and then we go in the opposite direction to the gradient, and then we scale it by the learning rate, which basically gives us an indication of how confident we are. And learning rate is set in the optimizer, which we define as 0.001. All right, I am going through all the questions. And yes, there will be a certificate granted upon completion for people who was asking, and the recordings will also be uploaded, as well as the slides, as well as the notebook, so people to go through on their own. So do you have to import the actual or ground truth values as a data set? Yes, so that's a good question. So I don't know if it was clear. So for example, when in my dataset class, in the get in the init function, basically we load in the image, and how the image is structured is that it's it's probably easier to see it here, is that this is a training set and your testing set, and then every image of a 0 is under the 0 folder. Every image of 1 is under the 1 folder. So if it actually opens up, we'll see something. All right, but yeah, all of the 0 images are on the 0, all of the 1 images are on the 1. So if we look at how we pre-process the data, is that once we get all of the images under this folder, we append the file name, which allows us to open the images, and we also append the folder name, which gives us the label And then when we output the get item, we return the image as well as the label, which is what we use to which we feed into the loss function to compare to the output that the model gives. So the process for calculating the best learning rate to use is essentially what you do is that this is the importance of your, what we call a validation set. So we take a percentage of the training set, and then we essentially try what we call hyperparameters. So basically we try a bunch of learning rates, and then we sort of measure the loss, or we measure the accuracy, and then depending on, we just choose the best one essentially. So like people get some intuition after playing with these stuff for a while. If we use the Adam optimizer, the standard one is 1e to the minus 4, which is about 0.0001, and that's a good starting point. But you sort of just like try a bunch and then see which one gives you the best value, best performance based on your application. Difference between Python and PyTorch. So Python is the programming language. PyTorch is built upon Python, and it is a package that allows you to train neural networks. So difference between loss and accuracy. Loss is essentially what is the signal that the neural network uses to update its parameters. Accuracy is related, but it is a human interpretable measure to give us practitioners or us users an understanding of how well the model is doing. So generally you want the loss to decrease on your training set and the accuracy to increase on your validation set. What does J represent in the formula? J is your loss function, is the output of the loss. And it's the average loss over all of the examples in your training set. So in this case, we're using the cross entropy loss. So essentially, this is the ground truth of the actual value, and then we get the log of the predicted value of the model, and then we average it across all of the examples in the training set. And that is the loss, and then you use that to optimize the parameters, because you use the loss to calculate your gradient. As you can see here, you get the computer gradient. So difference between PyTorch and PyCharm. So PyCharm is an editor. So it's what you use to write your Python programs. PyTorch is a framework in Python to train and debug neural networks. The recordings will be uploaded on the website. And each digit image is again 784 pixels, which is, as we said, we standardized these stuff before, so it makes it easier to process and train these neural networks. So someone asked, OCR readers do this activity. So it's actually interesting. So the OCR readers, so for example, the MNIST data set that we were looking at. So this actually, I can give you all the backstory, which is actually pretty fascinating. So this was a data set that was used to train current OCR readers, actually. So the current head of Facebook AI worked on this model called convolutional neural networks that you're going to look at on Wednesday. And it was trained on this data set, and it was that technology that was used to process banking, to process checks in the 1990s, and is sort of the foundation of most OCR readers. And yes, a certificate would be distributed at the end of the course. How the hidden layer numbers are selected. So that is similar to like the learning rate, which we have to sort of try a bunch and see how they perform. the hidden layers are also a hyperparameter which we have to test and see what works best. So I just chose 1,000 just to get people the intuition of how these stuff work. There is an optimal number depending on your data set and your application. You just gotta try a few of them to get some intuition. For people who are raising their hands, if you just post your questions in the chat or in the Q&A, it would be easiest. And the PowerPoint and the slides and the code will be distributed on the course website, I think today or tomorrow for today's lecture. So I could go through the code one more time since people, I think, maybe have a better understanding of what's going on. So again, NumPy, it's a library in Python that is used to do mathematical processing. PyTorch is another library in Python that's specifically designed for neural networks, particularly to train and to build and train neural networks to run on GPUs. It's developed by Facebook. And for those who actually come to all the lectures, there are some cool Facebook swag, but virtual swag, wallpapers, etc. that people give out at the end, etc. Yes, so this is the NumPy zeros tensor, NumPy array. And then this is a similar in PyTorch. We create 2 by 3, which is 2 rows, 3 columns. 2 rows, 3 columns. And this is all pretty much basics of going between NumPy and PyTorch. So PyTorch is built on top of NumPy. It just has a lot more sort of functionality to make it easier to work and train with neural networks. So this is all about sort of playing with NumPy versus PyTorch, etc. And then sort of the main thing I think is being able to sort of put PyTorch. So when you initially create a PyTorch tensor, it's on CPU, as can be seen by if you print its device. But if you move it to CUDA, and as I said, you have to sort of go to edit, notebook settings, and put it on GPU for you to be able to use the GPU available. And when you move it to GPU and you print this device, it's now on CUDA or GPU. And then we're going to use PyTorch to build and train a neural network to classify images from the MNIST dataset. And as I said, a classifier, what it does, it takes some image and it predicts what is the label. So given that this is a 2, it predicts, hopefully it can predict 2, it predicts these as 9. So we do a bunch of imports. Here we import a bunch of useful PyTorch functions. And then Torch Vision is particularly used for computer vision. And these are a bunch of other useful functions, and the NumPy and PIL, which is used, PIL is used particularly for image processing. And then, as I said, there are like, as I said, basically 5 main steps you got to think about in most applications. You create a data set, you create a model, you define your loss function, your optimizer, which optimizes the weights, and then you actually train your neural network. So here we define a PyTorch dataset class. And essentially the main function you got to look at is init, which does some initial preprocessing, as well as the get item function, which essentially defines how you want your data to be outputted. In most cases, you want an image and the label associated with the image, which is essentially what the get item does. And then this is the length of a data set, which is basically the number of examples in the data set. Then we have to define what we call a data loader, which essentially takes in a data set and specifies how many images per iteration you want to look at. And then we want to shuffle the data so that the model does not, the model sees images, different iterations. We define a training set as well as a testing set to measure the performance. Here we visualize the data set. As you can see, it's a bunch of just handwritten digits. We define the model. Here we use an input layer of 784, which is the size of the image, which is 28 by 28. We have one hidden layer neural network, which we define as 1,000, and our output is 10, which is the number of digits in its 10-digit output. So you want to compare the probability distribution of what the neural network outputs versus, say, the probability distribution of the labels. And here, neural network is very simple in PyTorch. So 784, 1,000 hidden dimension, then 1,000 hidden dimension to the 10 layer output. This is the activation function that we looked at previously, which is the ReLU activation function. As you said, the importance of activation functions are to introduce nonlinearities in the model to classify nonlinear data. We moved the neural network onto the GPU. We define a loss function, which allows us to compare, which in this case we use a cross entropy loss, which compares two distributions. Then we have an optimizer, which takes, as I said, the model parameters, learning rate, on a high level mostly. And then so most training loops look like this. You go through the data epoch number of times. Then you have your data loader, which gives you a batch of data and labels. You move it to GPU, you pass it through the model, you define the loss, which is basically comparing the model prediction with the target or the ground truth prediction. This basically tells us how bad or how good the model is. We calculate the gradient, which is, as we've described before, is essentially basically this does that. Loss and backward gives us this gradient for each of the neural network's weight parameters. It's usually pretty complicated, but PyTorch does all of this stuff for you in the background. And then optimizes then optimizes the weights of the neural network by factoring the learning rate and the current setting of the weight parameters. And then we define our testing function, which is run every epoch to measure basically every time how well our model is performing. We train the model for 5 epochs. We want the loss to decrease, which it is. We want the accuracy to increase on the testing set, which it is. So that means it's doing something right. And then we can then look at, after we've trained the model, we can look at how it is doing on some example data. And in this case, it does, if we randomly sample again, it seems to be mixing up. Here it's wrong, It seems to be mixing up 7 and 5. Yeah, so its accuracy is about 80%, which is okay. But once we look at convolutional neural networks, it would get to 99%. So let me answer the last few questions. If anyone has any more questions, please post in the chat, probably easiest. Personal preference towards PyTorch, why not TensorFlow? I work at Facebook, and we develop PyTorch. So personally have to use PyTorch. I also just think PyTorch is just much better. And TensorFlow has sort of, has sort of lost its appeal. I think PyTorch is sort of the de facto language and de facto framework, I would say. So are there optimal ways to find are there ways to find optimal parameters for particular domains? Yes, there is like grid search. it's great to just random search. Yeah, it's just a matter of, it's a lot of convenience functions which you could use sort of to sort of like automate sort of selecting and optimizing hyperparameters. We don't go into this in this course because it's more for just like getting these models to work really well, while the course is more geared to sort of introduce a lot of high level concepts and how to play with these ideas. So yes, so sigmoid and ReLU are sort of layers to basically help. So basically, as we've sort of shown here, that most data is nonlinear. Nonlinear meaning that a straight line cannot separate the different sort of, cannot separate the data into sort of structural categories. So as you can see here, you need to have what we call a nonlinear function sort of with the data. And if you look at if you do not have this activation function here, this is just a linear operation. It's a summation plus a multiplication, which is a linear operation. And if you stack a bunch of just linear operations, it's just a linear function. So adding the nonlinear activation function here, which sigmoid used to be the popular one, but now it's the ReLU activation function. So sigmoid squashes values between 0 and 1. ReLU is basically gives you the maximum of 0 and the current value. So it's just basically 0 less than 0, and then a straight line identity mapping above 0. So yes, so when you look at the neural network, actually we could quickly show this actually to give you a sense actually of the importance of that. We could essentially just only do so here I'm taking out the ReLU nonlinear activation function, and I'm going to retrain the network and see what the accuracy is. So we got an 81% accuracy last time. Oh, sorry. All right, while that is training, I'll answer more questions. Oh, the model parameters have already been trained. Let me restart runtime. So yeah, while that is training, so the type of neural network I use is what we call a multi-layer perceptron. It's just basically a bunch of these what we call perceptron units stacked together. So as we're looking at here we have 728, and then we have 1,000, and then 10. And it's just all of these are just little perceptron units, which yep, it takes some input, it weights the input, and applies nonlinearity to give you the output. So people are asking how to use the notebook. It's pretty, PyTorch should be installed automatically in the notebook. This notebook works out of the box. You just need to do file and then save a copy in Drive, and then you could play with it yourself. You could, and I encourage people to try. Different settings to try, different activation functions, different hidden units, increasing the number of layers, seeing whether they can get an increase in accuracy, etc. And it all works out of the box. Make sure you enable GPU. And if you need to install any extra packages, you could just do pip install and the name of the package. But yes, Colab should come with Python and PyTorch pre-installed. So you don't need to, like, once you have a Colab, so like once you have a Google account, you can make your own Colab. So you can just go on Colab research.google.com. And once you have a Gmail account or a Google account, it's pretty trivial. You just do new notebook, and yeah, you could name it, you could import Torch, and it should work. And yes, and then you could make it support GPU, and it will restart. It's connecting again, and then once it has reconnected, then you could run it again. So we would touch on time series forecasting in lecture tomorrow actually, and then convolutional neural networks on Wednesday, and GANs on Thursday. Sweet, I think that is it for today. If you all have any questions, feel free to reach out via email. And yes, we will post all of the lecture slides and the Colab notebook in case people didn't get it, and also the recorded lecture on the website later today. Thank you. And if you have any questions or concerns, please feel free to reach out. Thank you.